We now consider the mechanical methods for nanomaterials elaboration, which are called high-energy ball milling. Here you can find a number of milling devices, going from industrial scale devices to in-lab devices. All of them are based on the principle of having balls that move around inside a cavity and which are all going to interact with the powder of the material that we want to mill. And then what changes from one model to the other is just the way that we are going to use to make these powder and milling balls interact. So we have different devices, as this attrito type mill, which is like mill apps which are turned around. You have horizontal ball milling, so you can see this is going to move, and these pieces here are going to make all the balls and the grains interact. Vibratory mill, so this is moving up and down, and the ball smashes the powder. Very popular one is the planetary mill. So you have here two cavities where you have your sample and the balls, and then you have two axes of, it's like planet. They turn around the sun, so this is the axis of the sun, and then around their own axis, and this creates a random movement of the balls. These are the type, and you see some examples here of picture of such devices. So some precautions need to be taken when you use energy ball milling. First, you are going to reduce the size of the crystallites, then to increase the number of surface atoms that can interact in particular with oxygen. So you need to be sure that either your sample is inert or in the presence of oxygen, or then to use an inert atmosphere like nitrogen or argon to avoid oxidation if you don't want it. And the other thing is that the work done by the ball mills is going to transform into heat, and so the temperature can increase and modify the evolution of the microstructure or nanostructure, and also the crystalline structure of the material. So if temperature plays an important role, then you need to stop from time to time the milling and to start again, just to leave the sample cool down. So the idea is to start from a microcrystalline structure and just apply mechanical forces, break the crystallites, and arrive to a nanocrystalline structure. The fact is that the balls here interact with the crystallites. There are two opposite phenomena that can take place: fracture, that is what we have imagined already, but also coalescence. So there are then two reasons that are going to limit the mechanical grinding. One is, as we have said, welding of small particles into clusters, so this phenomena of coalescence. But also when we are going to reduce the size of the crystallites below 50 nanometers, we will have mostly single crystalline particles, which are more difficult to break in general because there are no interfaces. Here we have an example of the evolution of the particle size, and here it is in micrometers, as a function of the milling time. And you see that we observe the competition of the two phenomena. If we start from very small size, here is a thallium and nickel alloy, then the size increases, and at a given time, here after a couple of hours, the size starts to decrease. So we have a big beginning, mostly the formation of larger particles due to coalescence. And then these coalescent particles start to break, and we can reduce further the size. So if we start from here, for instance, ball milling will be pretty efficient. We have to wait 5-6 hours, and then we get much smaller crystallites. Starting from here, will be perfect because from the beginning we start to reduce quite rapidly the size. But if you start for something like that, ball milling is going to be useless because after days of milling you will get exactly the same size. Different phenomena can take place between milling. One is phase transformation, crystallographic phase transformation. Here you have the case of a sample made of niobium, that is BCC crystal, and after extensive milling, here you have the number of hours, we start to see some new peaks which corresponds to the FCC phase of niobium. So we have a phase transformation, and you see that also at the end we start to see a new peak corresponding also to iron. So you have at the end niobium in FCC structure and also the presence of iron, which this iron that appears just from the beginning corresponds to the pollution by the milling machine. So these are facts you have to consider. Another phenomenon that can take place is amorphization. In some cases, here nickel zirconium alloys, after extending milling, here you have the times, half an hour, 25 hours, 73, 165, and the corresponding Laue diffractogram, and you see that here we have single crystallites, and afterwards we get something that looks like a structural S. This corresponds to the amorphization. So high energy ball milling can modify grain size, the morphology of the crystallites, their composition. You can, for instance, mix two different materials to alloy or leave for oxidation. We can have crystalline structure modifications between different phases, or even amorphization. And at the end, in any case, you need consolidation, and this can be done by sintering or hot extraction. One example of industrial application is the production of zinc oxide nanoparticles that are very much used in cosmetics because they are wood absorbers in the UV domain. So as it can be seen here in this information given by the producer, by the company, the powder is ball milled to get a smaller size, then mixed with other organic materials to get the final product. And you have here a distribution function centered about 25 nanometers of zinc oxide particles.